Our senior design project was sustainable vertical farming using abandoned malls. Our team consisted of Madison Driscoll, Martini Nostroza, Caitlin Malloy, and Benjamin Martinez, all from chemical engineering. Our project number was 19140.
The problem that this project attempts to address is that the human race faces a challenge of a rapidly growing population with only a finite amount of land to service the food needs for this growth. Another problem is that as a result of cheaper land and labor in different countries, the average distance conventionally grown produce will travel to get to your plate is 1,494 miles. These are called food miles, which are environmentally harmful when accounting for the carbon footprint of transportation. Our project goal is to design a vertical farm using abandoned malls, which will produce 3 different types of vegetables and fruits to meet the consumption of at least 8% of the population for any given city for 25 years, utilizing an aquaponic system and renewable energy.
Materials and methods. Our vertical farm uses an aquaponic system, which is a form of vertical farming that combines hydroponics and aquaculture. Hydroponics involves cultivating plants in nutrient-enriched water and is a soilless form of agriculture. Aquaculture involves farm-raising fish. The water from these fish tanks is used in the hydroponic system, and the fish waste provides the necessary nutrients in the form of nitrogen, phosphorus, and potassium. An aquaponic system is typically indoors, so there is no need for pesticides, and there is complete temperature control, so vegetables can grow despite harsh weather conditions. The aquaponic system we are designing is modeled from Foothills Mall in Tucson, Arizona, so the production rates were calculated using Tucson's population. While Foothills Mall is not abandoned, it is used to model the system so these methods can later be applied to various abandoned malls across the United States as an alternative use to the infrastructure. We decided to grow head lettuce, strawberries, and tomatoes in our aquaponic system, and these vegetables were chosen because they were the top-selling non-rooting vegetables in 2017 according to the USDA. Non-rooting vegetables are compatible with soilless hydroponic systems. There are various methods to grow vegetables in aquaponics as long as they are soilless. Grow beds, shelving units, and vertical towers are compatible in hydroponics. Vertical towers were used to grow all of the fruits and vegetables as they optimized land usage. Vertical towers have vertical plastic tubes where the nutrient-enriched water is pumped through. In addition, tilapia was chosen to be the fish to be raised since it is the most common fish in aquaponics. This is because they are very resistant to disease and temperature changes. These fish can also be farmed and marketed. The vertical farm maximizes renewable energy. The farm was chosen to be completely powered from solar energy. The solar energy can be gathered by placing solar panels on the mall's roof. In addition, energy-efficient LED lights are used to provide the plants with artificial sunlight. Once we made these decisions, we were able to design the vertical farm. Figure 1.1 shows the vertical towers growing plants in a vertical farm system, and Figure 1.2 shows an industrial-sized fish tank.
For the design, the team decided to research some constraints for the vertical farm to function properly. Some initial specifications that we decided to base the energy and mass calculations off of were that each plant has an 80% nutrient uptake of nitrogen, phosphorus, and potassium from the water mixture coming out of the fish tank. The total ammonia nutrient concentration must be less than 1 ppm to prevent the fish from being poisoned. The fish tanks need to be on the ground floor. Each tower need 1 gallon of water per hour. Each tower can hold up to 51 plants, and the average height of the shopping stores in the mall was 12 feet. The capacity of the vertical farm was based off the number of plants that needed to be planted, which were 283,876 strawberry plants, 665,225 lettuce plants, and 350,210 tomato plants, each with their respective number of towers. The vertical farm takes up all of the indoor area of Foothills Mall. The vertical farm area was about 14.23 acres, and the total growing area was 11.48 acres. The other area was occupied by the fish farm, staff area, termination area, and shipping area. There will be a pump for every 10 fish tanks to make the process more economically feasible, which ends up being 50 pumps. The number of fish tanks were calculated by the amount of water the towers needed, which ended up being a total of 493 1,868 gallon tanks. Table 2.1 shows the water and nutrient requirements for each of the plants. Figure 2.1 shows the mall roof space that can be used for solar panels that we took from the NREL solar calculator. And figure 2.2 demonstrates the process flow diagram of the watering system. In the PFD, the water mixture from the fish tank goes into the grow bed of each plant, and then the clean water that comes out of them is recycled back into the fish tank. The city water coming in accounts for any water loss to the plants to keep a steady tank level. There is also a control valve to evacuate the system if the ammonia concentration goes over 1 ppm.
Looking at the costing in the results section of our project, the total capital investment of the vertical farm was about $33 million. The annual sales of the products of the vertical farm, which were strawberries, tomatoes, lettuce, and tilapia, were about $11 million. The vertical farm first became profitable at 24 years. At the end of our costing, which was at 25 years, the profit was about $1.3 million. After designing the vertical farm to optimize the land usage, we were able to increase the production to meet 27.72% of the consumption of lettuce, tomatoes, and strawberries in Tucson, Arizona. The production rates by product were calculated. There were about 1.1 million pounds per year of strawberries produced, about 2.9 million pounds per year of tomatoes, about 2.2 million pounds per year of lettuce, and about 249,000 pounds per year of tilapia. The energy usage for our vertical farm was calculated using literature values for aquaponic vertical farms. The energy value was scaled around the capacity of our vertical farm and was found to be 3.07 gigawatt hours per year. The DC size for the solar panel system used to power the vertical farm was 1,814 kilowatts. The water usage for our vertical farm was found to be about 11 million gallons per year. The water was used to water the plants and replenish the water in the fish tanks.
In conclusion, we produced enough strawberries, lettuce, and tomatoes to meet the consumption of 27.72% of Metro Tucson, utilizing all of Foothills Mall, which is greater than 8% of our original goal. We're also profitable at years 24, which is sooner than our 25-year goal. And using only a portion of the roof space available, our vertical farm is capable of being completely powered by solar energy. Here are the references for some of the data that we included on this poster. We would like to give a special thanks to our mentor Yadi Wang and our professor Dr. Adriana Brush for their guidance in our project. We'd also like to acknowledge the vendor at True Gardens and our representative John Fairclough for providing us information about growing towers and costing. Thank you.